Hi folks, Chris McCarthy here at SS State. I'm going to try to solve this problem from Walker's textbook, Physics, Volume 2, and it's on a double slit problem. So double slit interference of light. It doesn't say that, but let's just read the problem and glean what we can, first of all. It says monochromatic light passes through two slits separated by a distance of 0.0416 millimeters. If the angle of the third maximum above the central fringe is 3.65 degrees, what is the wavelength of the light? So a lot going on there. Let's just break it down. Monochromatic light, you remember that just means laser light, only one color, like a laser, and it passes through two slits, so that suggests a double slit experiment is going on, and the slit separation is given in millimeters, and then they're asking for the wavelength, and usually we express wavelengths in nanometers, so we might have to do some unit conversion here. So let's take a crack at it. I've got a whiteboard here, so let's see if we can put that to use. And I've drawn the double slits right here. Light's coming from here. It's going to go through two slits. And you remember, light is a wave, so there will be two waves. And depending on how they hit this screen, those two waves will either interfere constructively or destructively. Which kind of interference do you think is going on in this problem? You can kind of tell there's a clue in the problem. It says the third maximum. So if there's a maximum more light, that means the waves are interfering constructively. The information of the problem actually gave us the slit separation, and that was D. So I'll just mark this as D. And with a problem like this, I like to sketch it out first. These light waves are going to interfere, and they'll produce a pattern on the screen. Maybe I can draw it in color. It shows up. There'll be a central maximum, and then there'll be a minimum, and then there'll be the first maximum on either side, and then the second maximum, and then the third maximum on either side. So the nomenclature we use for these maxima and the minima, we number them with integers. M equals 0 for the central maximum, M equals 1 for the first, 2, and 3. So that would be the third maximum. And they give us an angle. The angle they give, we'll call it theta. And by that they mean this angle here. The angle from the center line up to that third maximum. And so I'll just draw that angle in as theta. So that defines the problem for now. And the next thing to think about is, well, what relationship can we find between these quantities? And we saw in class that a double slit experiment has a particular path length separation. The path length separation for a double slit is d sine theta. We saw that in class, so I'll write that up here as delta L. Path length separation is d sine theta. We derived that in the lecture. In the case of constructive interference, we only have constructive interference when the waves are an integer number of waves separating each other. In other words, this path length separation, delta L, is an integer. So that means for the double slit experiment and for constructive interference, constructive only now, we can write d sine theta as an integer number of wavelengths. And we'll use the letter m as to represent an integer. It is always an integer in this context. And lambda as the wavelength. So we have the slit separation is given. The angle is given. What about m? Is m given? They didn't say m equals something, but yeah, we have that here. On the screen, the m is just the integer that represents which maximum we're talking about. So m is 3. So we've got that. So we can solve this equation for lambda, and that will be the crux of the problem. So divide both sides by m. We would get lambda, the wavelength, equals d sine theta divided by m. And that's the key solution to the problem. Now, if I were looking at the slit separation, d, it's given in terms of millimeters. And if we want to produce a wavelength, lambda, in terms of nanometers, we'll have to do a conversion. So let's do that. Let's see how many millimeters it was given as. All right, so we were given that d equals 0.0416 millimeters in my version of the problem. Can you convert that to nanometers? Well, if you don't know the conversion between millimeters, nanometers offhand, you can use meters as an intermediary. Meters, of course, is the standard conversion, or the standard unit of measure in the metric system. And a milli is 1,000, so there are 1,000 millimeters in a meter. So that's a conversion we can do. Cross that out. And now this is dividing by 1,000, so that's a factor of 10 to the minus 3. I'll just carry this through here. We have d equals 0.0416 times 10 to the minus 3 meters. And now let's convert this to nanometers using another conversion factor. These conversion factors are really handy for converting units. In this case, we want to cancel out meters, and 1 meter is 1 billion nanometers. That's how small a nanometer is. 1 billion is 10 to the 9th. So 10 to the 9th nanometers, nm, is equal to 1 meter. So we can cancel that out, and then we could put all this together to solve for d in a more compact way. We would get d equals, going to keep this, 0.0416 times 10 to the minus 3 times 10 to the plus 9. So 9 minus 3 is 6. So this would be times 10 to the 6. And then that's nanometers. And then we could use that in our problem right here, and then multiply through by the sine of the given angle, divide by m equals 3, and then we would have our wavelength in nanometers. So that's how I do that problem.